Hi folks, Chris McClure here. We're going to now talk about solving inequalities which involve polynomials or rational functions. Now, we've already had a discussion in dealing with inequalities. Solving inequalities, what are we talking about? We're finding the values of x which will make the inequality a true statement. It just happens that for these inequalities are going to be involving these special functions that we've been studying the last several sections, polynomials and rational functions. Now, there's two basic ways that we could solve inequalities involving these functions. One way is to graph the inequality, and the other way is to solve the inequalities using just algebraic techniques. So we'll see both of those techniques. So this first example is going to show you how to solve this inequality involving this polynomial just by looking at the graph of it. So here's this inequality here that we would like to solve, meaning for what values of x will this inequality be true? What values of x will this function be less than 0, where you can let f of x be equal to this function, as we've seen here. So go ahead and graph this function. And you know how to graph this function, so I'm just going to kind of go on through here, find your intercepts, x-intercept, y-intercept, and then plot the points and plot the graph, figure out your end behaviors, and so forth. And you plot the graph, and then ask yourself the question, where's the function's graph below the x-axis? And of course, that's going to be over here. So we're talking about for all values of x less than -1. Less than -1, not including -1, because at -1 the function is equal to 0. But when x is less than -1, this whole thing right here will be negative. Just like you see in the graph here, when x is less than 1, the graph is below the x-axis. Same thing, folks. So that's how you can use the graph to solve the inequality, just by looking to see where the graph is under the x-axis in this example here. Then this, of course, either one of these pieces of notation will allow you to express the solution to your inequality. Either x could be such that x is less than -1, or just on the interval from -infinity to -1. Either way, you have the solution there. All right, moving along here. Here is yet another example of how we can solve an inequality. We have got x to the fourth greater than x. So what values of x will it be such that x to the fourth is greater than x? Well, our technique is going to be where you move everything over to the left-hand side and then graph that function. So here we've subtracted x from both sides, and let's graph the function x to the fourth minus x. And of course, you know how to use your graphing techniques. Find your x-intercepts by factoring the function, just like we've done here. And 0 and 1 are the two x-intercepts, and so forth. Your y-intercept will be 0 as well. So we can go ahead and do like we've done already, is, you know, after you've divided up the x-axis into those, you know, 3 intervals, demarcate it between 0 and 1 and beyond to the right and to the left of 0, and pick convenient test points like -1, 1/2, and 2, and look at the values of f, meaning your function, at those 3 test points. And then determine that, hey, because of the fact that the function's not going to, you know, switch between being negative and positive on those intervals, if the function is negative at one point on this interval right here, for example, it's going to be negative for that entire interval, and so forth. That's the same sort of logic that we use for these other two. So we could say, hey, the function's going to be negative here, but not here, and not over here as well. So the function will be negative over here, but it'll be positive over here. it looks like it's going to be 0 there. So on the interval from 0 to 1 and on the interval from 1 to infinity. So what's the solution? Actually, the function is positive here, negative there, and positive here. So the function is going to be positive on this interval here from negative infinity to 0 and from 1 to infinity. But not here, because when we evaluate your function of your test point, that worked out to be negative. So all of f is negative here. So to the left is 0 and to the right of 1. So you could graph your solution like on a real number line, or you can just write your set builder notation, or just use your set notation as in your interval notation from negative infinity to negative 2, unioned with 1 to infinity, just like you see there, or just like you see here. All right, moving along here. Solving rational inequalities. Now, these inequalities involve rational functions. So the technique here is to make sure that everything is over to the left-hand side of the inequality, and on the right-hand side you've got 0. So what we'll do is we'll go ahead and graph the function x to the x squared minus 4 over x squared minus 9 by looking at asymptotes and intercepts, which you know how to find now, so I'm going to go ahead and skip ahead. So your asymptotes will be at plus or minus 3, and your y-intercept is at 4/9. Your x-intercepts are at negative 2, 2. So plot all those points and those intercepts and asymptotes and stuff. And then you can go ahead and graph the function, and then ask yourself the question, for what values of x is the function positive? Meaning, where is the graph greater or above the x-axis? And of course that'll be to the right of x equals 3 and to the left of x equals negative 3. So those two intervals make up the set of solutions. Oh, don't forget about this interval is here between negative 2 and positive 2. So between negative infinity and negative 3, between negative 2 and positive 2, and between 3 and infinity. So kind of a complicated solution here. Now, let me just make the point that we have a greater than or equal to sort of inequality. So we have to include x equals negative 2 and x equals 2 in our solution, endpoints of this interval right here. And so any x value in the union of these three intervals will make the inequality a true statement. So here's your solution, either in set builder notation or in interval notation. Let's go ahead and graph, or at least solve this inequality. Solve this inequality. We don't necessarily have to graph this. We could just solve it algebraically just by moving the 3 over to the left-hand side, and then combine like terms by getting the common denominator of x plus 2, like you see there. And then multiply the 3 times the x plus 2, so you get your minus 3x minus 6, and then combine that with the 4x plus 5, like you see there. Simplify, and you get this inequality. Now you are going to have an x-intercept of 1 and a vertical asymptote at negative 2. So what you'll do then is split up the x-axis into 3 intervals as demarcated by these 2 points. So go ahead and draw your horizontal line with an arrow at the right hand tip and plot those 2 values of x, and then pick a convenient test point on each of these intervals. Like at -3 here, f of -3 is 4, so that means the function is positive. And 0 is our test point over here, and f of 0 is negative. That means the function's negative entirely on this interval, from -2 to 1. And then pick maybe 2 as a convenient test point to the right of 1, and f of that number is a positive number as well. So we see that the function's positive to the left of -2 and to the right of +2. And so that tells, now let's go back real quick. It was really this inequality that we were solving, which is equivalent to this one. So the solutions to this inequality will be exactly the same as the solutions to this inequality. So we saw that the values of x, which will make this function greater than or equal to 0, will also solve this inequality as well. So let's go ahead and review. From -infinity to -2, including -2, well, hold on here. We can't use -2 because of the fact that at -2 the function will be undefined there. So we will not include -2. Sorry about that. But we will include 1 though, because the function is defined at 1. And indeed, when you plug in 1 for x here and here into the original inequality, you get 4 times 1 is 4, plus 5 is 9, divided by 3 is 3. So 3 is greater than or equal to 3, that certainly solves the inequality, plus all numbers greater than 1. So here's your solution here. A little bit tricky with that -2. I almost fell for it too, but just understand that this function right here is undefined at -2. By the way, if you're curious as to what this symbol here means, this upward facing cup right here, that means union, as the union of these two sets. That just means that your value of x is either in this interval or in this interval, not both. Okay, so that's it, I think. By the way, if you wanted to graph the solution set, there you are right here, where you place this little open parentheses facing to the left at -2, and of course, and shade it to the left of there, and place the square bracket at +1, and shade it to the right of 1. So here's kind of the recipe for solving your polynomial and rational inequalities, and I can summarize it for you real quick. Move everything over to the left-hand side of the inequality so that you have 0 on the right, and simplify the expression on the left, and then find out where your zeros and your asymptotes are, and plot those on a real number line, and evaluate your function at convenient test points and the intervals in between, and then select the intervals which will satisfy the inequality. Okay, so that's it for solving inequalities involving polynomials and rational functions. All right, the next lecture that I'll record shortly will be involving solving polynomial functions, which is the same thing as finding real as well as complex zeros of polynomials. Okay, so stand by for that. We'll talk with you later.